We'll go ahead and get started on time. On my clock, it's 7:40, and we've got an hour and 20 minutes to go over a lot of material. So if I can get my slides working. So in this section today, in this lecture today, we're going to go over the concepts of stream computing. So we've covered the concepts of parallel computing, and now we're going into stream computing, and these are the ideas behind what you'll be implementing in code. So we'll start with our good old friend MapReduce. You guys remember we've been over this a couple of times of how an input is split, mapped, shuffled, and reduced, and final results are produced. And this is a way of doing parallel processing at scale. And this pattern is applied over and over and over again. Now, there are some problems. There's some really good things about MapReduce. You know, it gave us the Hadoop distributed file system. It allowed us to work in distributed and massive parallel and to accomplish things that were impossible before. So it really took parallel processing out of the laboratory, out of the university, and into the IT departments of companies. Hooray for MapReduce. But there are some limitations. The first one is that you're dealing with a finite data set. Yes, it's a very, very large data set. It could be petabytes, but it has a beginning and an end. And you are always working on it in a batch process. The process starts and the process ends. And what happens is we started chaining these processes together. We started taking the output of one and making it the input of another. And we'd have MapReduce, 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 which led us to all these complicated workflow infrastructures that we touched on, Uzi and Azkaban and Pinball, et cetera, to where we started making these graphs of map flow steps, which, as we talked about, led to the advent of streaming frameworks. And here are some of the most popular ones. We got Spark, Storm, AkaStreams, Samza, Flink, etc. It was just an explosion of this because everybody was trying to solve the same problem. So that's history up till now, what we've covered, right? And so what we find are streams are everywhere. They're a very common pattern to data. Stock market trading, social media, sensors, weather, transportation traffic, which is you can think of that as social data and sensor data together. Video is, whenever you're processing video, it is a stream process. And if you're dealing with artificial intelligence, machine learning of vision, computer vision, you're dealing with a streaming problem, right? And even with the stock market, I don't know if you guys are familiar with this movie, Trading Places, but the trading on the stock market floor stops at a certain time on a particular market. And as a result, companies always deal with a end of day kind of processing, this batch processing, where they say, okay, let's take all the trades of the day and sum them up. But in reality, that's no longer reality, because somewhere at any time the stock market's open. And so the trading never stops. So companies have found that dealing in batch does not reflect reality. They're always trying to impose a false reality onto the data and onto the system, which always gets you in trouble. So here's the fact, right? The real world never shuts up. It never pauses. It never stops. So why would our compute processing? If the world doesn't operate in batch, why would our computing solutions for the world work in batch? And the fact is, they don't. Whenever we try to impose batch onto the world, we run into problems. We always run into shortcuts. We always run into customers' expectations are not fully met. So how do we program in streams? And that's what we're going to talk about, because all of our traditional training, if you think about it, is done on batch. We always work with finite data, and now you're going to be dealing with infinite data. Well, the first thing to think about is these three patterns. These are the basic patterns that you use over and over and over again in stream processing. You have sources, sinks, and operators. Very basic concept. A source is anything that creates a stream of data, that creates a stream of events. A sink is something that consumes them. And an operator is simply something that is both a source and a sink. It consumes events and then produces other types of events, or consumes data and produces other types of data. I will use the word data and event interchangeably. What happens is we take these patterns and we combine them into directed acyclical graphs. So first off, it's a graph, which means not bar charts and pie charts, but a web of interconnected things. A graph has nodes and edges. This is a mathematical graph. It's directed in that the arrows mean something. That data flows from source A to operator C and not the other way around. And finally, it's acyclic, meaning that nowhere can you circle back by following the arrows to the same node, which means that no operator consumes the results of its output. This is very critical, right? Cyclic is bad. And for the most part, you will find that data processes follow an acyclic pattern. And whenever you find that you're dealing with a cyclic pattern, well, there's some far more advanced patterns that need to be applied than what we're going to cover today. Any questions about directed acyclical graphs? Pretty straightforward. Sources, sinks, operators, don't circle back. All right. So streams are different than regular programming in 5 fundamental ways. First, the data is infinite. You're continuous, and because of that, you're continuously processing. There is no concept of now. We'll touch on that. Fourth, you're dealing with eventual consistency versus a false sense of consistency. And I'll have to explain that. And 5, which we've already touched on, is because of all this, streams are much closer to reality. And as you know, reality is pretty messy. So first concept is unbounded. So we're accustomed to dealing with bounded data. We have a file, we open the file, we read through the file, we close the file. We have a table. We start a query, we scan the table for the query, we come to the end of the table, we give the results of the query. Those things don't apply here. So that is the first thing you have to get your mind around. And you'll find yourself, when you get started with this, you'll keep slipping back into finite patterns of thinking unconsciously. And you'll have to catch yourself. And the second that goes along with it is that compute is continuous. It doesn't have an end. And that's really where that's the challenge we really face, is it's always moving. So, and we'll touch on some of the particular issues of how to deal with that. So, for instance, as I touched on with the stock market, business as usual is that you're calculating the end of day balance, your closing balance for the day of trading. So you start with yesterday's closing balance, and then you add up all the events that occurred during the day from 9:30 to 4:30, from market open to market close. And then you publish your new closing balance. That was the typical way of thinking 40 years ago, or 30 years ago, or 20 years ago. But it doesn't apply now. So with streaming, you're constantly recalculating with each new event, and you're admitting a balance with each new event. So there is no stop trading, figure out the balance. It's just every single time there's a change, you just publish a new data, a new balance. And then if there is a need for a closing balance, because a lot of legacy systems, a lot of legacy legal issues and accounting issues expect things like a fixed time, right? We close the books on the quarter, we close the books on the year for taxing issues, et cetera. All we do instead of it being the result of a batch, we just arbitrarily pick one value in the output stream and tag it as the closing balance. And that value will be different a second before and a second after, because data is constantly arriving. Now, and we'll touch on that again. Thirdly is this idea of now, right? So in stream processing, there are three different times. There is the event time, the ingest time, and the process time. And typically, we just deal with the event time and the process time. The event time is when the event actually occurred or was measured to have occurred, to be more specific. It's when that physical event entered the digital realm. The ingest time is when the event is written to the system. So you can imagine that you have some field system collecting that has intermittent connectivity with the internet. It comes in and out of connectivity. And so it may be constantly recording, but it may have to batch up data to the system. So the event time, the recording time, and the ingest time, when it actually gets into the system, there may be a gap there. And there's most certainly a gap in the process time, which is when the event is observed in the system by a particular processor. And even if that is milliseconds or nanoseconds, it's going to be different. And as a result, you always have this issue of time skew in stream processing. Now, the ideal is that event time equals process time, but it doesn't happen. So there's always a skew between the process time and the event time. So what is now, right? If we look at our previous graph, you may have the sources are recording events at the wall clock time, 3 seconds after 3:07. But the operators are operating on the data that is 1 or 2 or 3 seconds from earlier that they received from the source. And then the sinks are operating 2 or 3 seconds after that. Now, of course, it's not going to be seconds across it could be seconds all the way end to end, depending on how complicated your system is. But generally, you're going to be dealing with milliseconds. But even so, it can become quite significant, depending on the complexity of the system, the volume of data, et cetera. And you'll have SLAs with your customer. Like if you're dealing with a trading system, you'll want if you're doing with a a fast trading system, well, this has to be, you know, nanoseconds. If you're dealing with a compliance system, then you're probably dealing with an end-to-end computation of 1 second. From the time the trades hit to the time you can see if there's been a fraud or something. All right, any questions on the fact that there is no now? You guys understand what I mean by that? All right. So there's only event time and process time in when you're dealing with this stuff. Then there's the idea of consistency. So as we talked about, in the old days, you'd have the trade date arrives. The trade date arrives at the end of the day. So you're the processor. The trade floor hands over and goes, okay, here's all our data for the day. And then you process end of day balances, etc. But in reality, you start with the previous closing data, and then you take these trades, and then you publish a new closing day balance. In reality, what has happened is after you closed the books yesterday, some corrections came in. They found some new trades. They found out they made a mistake, et cetera. So you've already had to update yesterday's end of day balance, right? Then you're taking this stuff and you're making it. And guess what? By the time you publish it, more corrections have already come in. So batch processes give us a false sense of consistency. And you've seen this concept of eventual consistency before. We talked about it in parallel processing, but we were talking about it in a distributed database sense, meaning in the CAP theorem, a distributed database can be consistent, available, or tolerant, but it can only be 2 of the 3. And you pick which solution you want based on the CAP theorem. And the consistency means that if I hit any one of the nodes, I'm going to get the exact same value. And in some cases, consistency from the data store is exceedingly valuable, is critical, right? So you would go with those kind of solutions. Whereas some others, it's not so critical. But that's what we mean by eventual consistency. Things like Cassandra and Dynamo, you may get a different value depending on which node you connect to, but eventually all of the nodes will have the same value. We'll get the update. Well, the same thing applies to organizations, right? So eventually in a streaming process, all the downstream processes will have that value. They'll just have it at a different time because each node in the stream has a different now, right? So in the old world, the batch world, around 6 p.m., all the systems will have the same value because sometimes we're a little early, sometimes we're a little late, but you know, it's around end of day, we'll get it all done, right? And it's wrong because what we had to do is arbitrarily create a time and more events came in afterwards. And we just said, no, stop the clock, we're stamping it there. In a streaming world, at exactly 6 o'clock to the millisecond, all the systems will have a value, but perhaps not the exact same value because their processing time will not match the event time. Now, some customers have a real problem with this because they're so trapped in this false sense of the false security of consistency. They don't want to accept that what they're calling consistent it may be consistent, but it's incorrect. And so there is a mental challenge for the end users to come across in adopting these systems as well. And it may seem trivial, but when you've got a lot of zeros going around, you know, if you're dealing with $1 billion hedge fund, you know, that eventual consistency may be plus or minus $1 million on the balance sheet. So just by when you time stamped it, the closing. So those are the 5 things that are different. Data is unbounded and infinite. We have continuous processing. There is no now. And as such, we're dealing with eventual consistency, which is much closer to reality. All right. Now with that, we're going to dive into 4 considerations that you have to deal with when programming. The first one is message delivery. The second is windowing, which is how do you deal with continuous time. The third is joins, and the fourth is scaling. I'm going to pause first and see if there's any questions. All right, no questions. So there are 3 types of delivery in a stream processing. The first one is at most once delivery, which can be called best effort approach. So you send out a message once and hopefully it gets there. But you never send out the same message more than once, which means that messages may get lost, but you never have a risk of double counting. And in some scenarios, this may be relevant. For instance, if you're dealing with a basic sensor, it may make sense to use at most once delivery from the sensor, because if you miss a couple of readings over a second, it's not going to impact things dramatically. This is the easiest delivery system to implement. The second one is at least once delivery. It can also be called guaranteed delivery. So here you have an operator sends out the first message, it fails, so it sends out a second message, and then it sends out a third message, which can be ignored. Now, this is the second easiest system to implement, but it will cause duplicates. You have to track as a processor what you've received. You don't want to count something twice. Like, imagine that a trade gets done twice. That would really screw up your balance. Another common example of how an operator would at least once delivery is if the operator was going along and then it crashed, and you're not really certain exactly when it crashed. It bookmarked. So a lot of times they'll bookmark what they've sent out. Every 20 messages, they'll bookmark, I sent out, I was at this point, right? And then they crash. And when they crash, you don't know where after that bookmark they stopped. So you go back to the bookmark and you bring the system back up, the operator back up, and it will undoubtedly send some duplicate messages after the bookmark. So there's a very common way of how you'll have at least once delivery. So that way you know downstream they got the messages, they just may have gotten them more than once. And that's an easier way for you to handle failure and recovery. But it puts a burden on the operators downstream. And then finally, there's exactly once delivery, which as someone that's building the business logic, this is ideal for you, right? You never have to worry about tracking what you've seen. You always know you're going to get every message, and you're never going to get the same message twice. Brilliant. But it comes at a cost, right? And it has to be implemented some way. The two most common ways is you have a distributed snapshot state checkpointing, like that bookmarking that I was talking about, but it's done across the entire system, not just at one operator. Or you have at least once delivery, and then the framework handles deduplication for you. So there's kind of a wrapper to your operator that's doing the transaction logging for you, and when it gets something that's already seen before, it just doesn't hand it to your operator, right? So this is just another example of Hurst's law, right? I don't know if I've touched on this in the previous lectures, but Hurst's law says that complexity can neither be created nor destroyed, it can only be displaced. So pay attention to where it went. In this case, if you have a very reliable framework that can handle this exactly once delivery for you, great. You put the complexity someplace where it's easier to manage. They took it off of your plate. It's not distributed in your business logic. It's just in the framework. But other times, you're displacing it someplace where it's even harder to track. So when somebody says, oh, look, I made it easy, always ask yourself this question, okay, then where did they hide the complexity? Is it in a good place, in a better place, or in a worse place? So that's delivery. The second concept that we have to talk about is windowing. So if you're dealing with processing time, you have to break, if you're dealing with an infinite stream, you have to break it up into chunks. You just have to. If you're dealing with a count, not so much. But how do you deal with something, well, how do you deal with count if it never ends? The count has to have some meaning in time, like it was X amount at time T. And how often do you announce that to the world? Do you do it on every event, or do you do it on every second? And then if you're dealing with something more like, what is the average? Well, that's averaged for what and for when? Windowing, you have to deal with windowing. So one way is you just do it by process time. You just say, when I get them, I'm just taking these things, I'll group 1 second of data, and then I'll process it. And then I'll group another second of data, and I'll process it. Another way to do it is do it by event time. And you'll say, okay, I'm going to take the processing events and group them into windows based on event time, so I can get a better understanding of the world. And I'll give you practical examples of this. And then a third one is session windowing. So there's three types of windowing, right? There is the basic frames. There is the sliding, and then there's the session. So fixed windows. Can we go with, yeah, fixed windows is the first one. I missed a slide, that's why I got thrown off. So the very first way of doing windowing is fixed windows. So you just take an exact time position, the same length, overlapping chunks of data. And you just box the data into these fixed chunks that are non-overlapping. So any event falls into exactly one window. And you can do this across streams. Because as I don't know if we touched on it or not, but a processor can be consuming one or more streams, and it may be emitting one or more streams. So, you know, processing by time into fixed windows, or you can process by events into fixed windows, which is a little bit more complicated. Then there's session windows, where you're taking a sequence of events and terminating them by inactivity within a certain time window. So what you'll do is you'll you'll watch the stream, and then if there's a pause of any significant amount, you group that together and say, okay, here's a session. And you pass it on down, you pass it into the processing as a session. You can think of that like activity on a website would fall. A user's activity on a website would fall within a session window that you may want to analyze all together. So here's a diagram of taking sessioning by event time. And the third one is a sliding window, which means that you have a fixed length and a fixed period. So you may be saying, let's look at the 10 seconds. We'll review the last 10 seconds every 2 seconds. So there, your fixed length is the 10 seconds, and your period is 2 seconds. So you're just shuffling along. And where that may take in account is, you know, has the temperature changed more than 0.1 degrees Celsius in 10 seconds? We may need to trigger alarm. Has the user pushed the button 3 times in 10 seconds? You may need to trigger alarm. And so think back to MapReduce for a second when you're thinking about windowing. So in MapReduce, what it did was it said, I'm going to give the reducer every value for a particular key, so that you'll be able to you'll now know the whole known universe of data. You'll have an array of data for that key, and you'll have all the values for that key, so you can do whatever it is you're processing. That was kind of like windowing, right? At the end, your processor had a boundary of data that it could do its calculation on. It was the input to the actual calculation. That's what the reducer gave you. With these different types of windowing, fixed windowing, session windowing, sliding windowing, you're doing the exact same thing. You're giving a boundary to the data for your processing, and you pick which one based on what it is you're trying to solve. Also, I'll note that a fixed window is is a sliding window that has the same value for fixed period and fixed length, if you think about it, right? All righty. So let's walk through a practical example. Here we have data that has occurred, and we've mapped the bottom is event time, and the x-axis is the event time, and the y-axis is the processing time. So we got a value of 5 at it occurred at 3, but we read it at 3:06, right? And you can think of these as milliseconds or seconds. Certainly not minutes, right? And you know, you can see how this occurs, right? So there's this number 9 that occurs right after the number 5, but there's a 3 second or a 3 millisecond, we'll just say second delay behind it, behind the 5. So at 3:06, we have processed, let's say we want totals over 2-second periods. And when I say second, I mean milliseconds, so just be easy. And so at 3:06, we have observed and processed this data. So we can say the value for 3:02 is 5, and the value for 3:04 is 7, and the value for 3:06 is 0. Then a second later, we have received a couple of more values. And so we now know, we have now processed that for the first window, the value is still 5. In the second window, the value is now 10. In the third window, the value is now 4. And so forth. Now we can observe for 308, because it is now 308. And we've, lo and behold, seen a value of 3. We've updated the second period to 18. And now we've said, now we've seen that 9, that 9 that came in late. And so we can say for the 302 that the value is actually 14, not 5, even though we're making that 9 seconds later. Now the question becomes, when do we tell the world our results? When do we actually publish that 14? Or do we not publish that 14? Or do we go ahead and publish a 5? Do we go ahead and publish a 5 now and then publish another 14 later as a correction? There's a lot of thinking you have to do about this. And this is a very simple sum that you're dealing with. It's, it can become much more complicated than this. So that's what windowing, that's the concept of windowing you have to deal with in stream processing is, okay, when do I tell the world, when do I know, even though I have an infinite stream, and even though I know because of different delivery cycles, you know, there may be at least once or best practice, best effort, message delivery that messages will come out of order. When do I tell the world my results? And it depends, right? So one of the ways that you can deal with this is watermarks. So we're not going to dive into watermarks, but the concept is that the system for you says all the input data for event time less than X have been observed. And it's a heuristic, it's a best guess, it's never perfect, but you gotta do it sometimes. So some of the streaming frameworks that we showed earlier provide watermarking for you, and some of them don't, and you have to implement it yourself. For instance, you may decide based on your experience that you watermark after 10 seconds with your system because 99.99% of the time I will have received all the data within 9 seconds or 9 milliseconds, right? So you're doing your own windowing based on a heuristic, based on observation. And maybe that 9 seconds is too long, or 9 milliseconds is too long. So you deal with these things on a case-by-case basis. All right, the third item that we have to deal with in streaming is the concept of joining, joining the streams. And joins are out there everywhere. I mean, this is part of streaming processing. You know, you're joining customer data with web traffic data. You're joining securities data with the trading data. You're joining weather data with transportation. You're joining 2 or more sensors, which is an example that hopefully we'll have time to walk through. And so consider this sample data, right? We have one stream on the left that is temperature in Fahrenheit based on zip code. And then we have another stream on the right, which is the weather encoded, like mostly clouded and that sort of thing. I don't know what these symbols mean, but that's some standard weather abbreviation thing, foggy or, you know, et cetera. And you want to join these, right? And the first number is a timestamp. So you're getting these feeds based on zip codes, based weather, and you want to join them, right? So we can visually start to see how the numbers start to line up. You're joining by the middle column. And we also can see how they can fall out of sequence, right? So for instance, the 12501 number on the left, the timestamp is out of sequence with the rest of them. So here's an example of, to start thinking about how would I join this data as I'm reading from these two streams. We're going to deal with a slightly simpler example. And this is the input data that we're going to go through to explain the different types of joins of a stream. So here you have views and clicks. And the views, you can see A occurs at 0 time, B occurs at time 1, C occurs at time 3, etc. And what does it mean to join these two data streams? Well, just like in SQL databases, there's different types of joins. There's an inner, a left, and an outer join. In SQL, you have a right join, but in streams, just deal with left joins, because that just means that one side is included. You just flip it to make it a right join to a left join, right? So we're going to talk about inner joins, left joins, and outer joins. So an inner join means that you admit an output when both input sources have records with the same key. Very clear, right? So if we were doing a stream, this is what the joint results would look like. So at time 0, we had an A event, and at time 1, we have an A event on the other stream. So at time 1, we can have a join of AA. Similarly, at time 2, we have a C event on one stream, and on time 3, we have a C event on the second stream, the view stream. So at time 3, we admit a join, and so forth. And notice B occurs at 11, but we don't admit something. And the concept here is that if you're joining stream to stream, there has to be some window of relevance, right? And so we're going to say that the window of relevance here is 5 time clicks. So no join would be admitted if we're doing a stream to stream join for B, because it's outside the window of relevance for an inner join. Does that make sense? All right. Now, sometimes what you're dealing with, for the sake of time, I'm not going to talk about table to stream joins. That's something you guys can deal with when you get into the K-streams discussions. I'm just going to focus on streams pure instead of streams and tables. But streams and tables calculations from the Kafka streaming framework make your life very easy. All right, so we're just going to focus on streams themselves. The second one we deal with is a left join. And that's going to be slightly different, right? So for the left join, for one stream, your primary stream, you're going to admit an event for every event on the primary stream, whether there's a join or not. If the other source doesn't have a value, then it just gives a null. So the left stream is your primary stream. For every event on the primary stream, it's going to emit an event, and it may or may not be augmented with a value from the other stream. So what that would look like. So here, our primary stream is views, and our secondary stream is clicks. So at time 0, an event A comes on views, so we emit A and null. And at time 1, a B arrives on our primary stream, but no B has has come on our click stream. So we emit B null, but an A has arrived. So now we can join that with the previous A value. So now we emit AA, right? Then at time 2, C occurs on the click event, but that's not our primary stream, so we don't emit any event. But at time 3, a C occurs on the primary. We see the C on the secondary. We emit CC join, and so forth. Do you see how this works? So the results of a left stream join are very different than from an inner stream join. And then lastly, and when you're dealing with tables, it gets a lot of, it's a different behavior. Lastly, an outer join, which is you're going to admit an event for any record that arrives from either input. And then they're just going to emit nulls on the opposite side if there's no equivalent value. Matching value, joining value, key match value. And so it looks a lot like the left join, except you're emitting events for every single time. And notice here that you still have this concept of windowing. Look at what B does. B at 1 emits, B at time 1 emits B and null. And B at time 11 emits null and B, because we've determined that it's outside the window of relevancy. Make sense? All right, so the joining of streams is it takes some time to get your head around it and working with it, and it just deal with it in practice. All right, and the last part of it is scaling. And how do we scale? We scale through being parallel. So we have, when you're looking at your DAG, your directed acyclic graph, what you usually deal with is the fact that, yeah, there is an operator, there is a source of type A, but there are many instances of it. And there is an operator of type C, but there are many instances of it. Say again?
Sorry, it was about something. It wasn't someone.
Was there a question?
No, it wasn't.
No, it was some technical issue.
Okay. All right, so we scale streaming processes just like everything else by operating in parallel, which means that your operators will be more than one of them. Sorry, I keep pushing arrow on the wrong screen. So one way to do it is to partition by source. So I may have I may have multiple instances of a source, and each source writes to its own stream. And then I might partition by round robin, which means I have a, are you guys hearing me okay? I'm hearing a lot of echo. Anyone that's on, that's not in the room, go ahead and mute. So here I'd say, you know, I want the output to be on 3 streams, but I only have 2 processors. So I'm just going to round robin my output. So as one instance, I'll write to stream 1, and then I'll write to stream 2, and then I'll write to stream 3, and then I'll write to stream 1 again. I balance that way. And the third one is the partition by key. So I, as a processor, if I have a key within range A to D, I write to stream 1. If I have a key between values E and M, I write to stream 2. And if I have a value between N and Z, I write to stream 3. So that, and each of the sources do this so that all the keys for a particular range are known to be on a particular partition. So what you're dealing with is here, the key concept here is that the sources are in parallel, the operators are in parallel, the sinks are in parallel, but also the streams between them, those arrows between them are also in parallel. So you're taking a stream and you're dividing it into partitions. And how do you do that? Well, there's 3 of them. You just do it by source, do it by round robin, or do it by partition key. What do I mean by key? Well, keys come in 3 types. There are natural keys. So the data that you're dealing with may actually have a natural key to it, like a place name would be a natural key, assuming that place names were unique. It may be a generated key or a surrogate key. You deal with these when you're dealing with SQL databases, right? That every time you insert a value into a table, the database will create a new integer that is unique for that row that you just inserted. And it's just a generated key or a surrogate key. And then there are composite keys where you take several natural or generated keys and you combine them to form a unique key, which is very common, to create a composite key. And there's 2 things that I would point out to you with keys. And keys will come up again and again and again for you in stream processing. Everything has to have a key. First off, one man's generated key is another man's natural key. So, for instance, in the United States, we get a social security number for tax purposes. Well, that's a generated key as far as the Social Security Administration is concerned. They just increment the number and hand the next baby a new integer, right? So it's a generated key for them. But for us, it becomes a natural key because we take that key with us everywhere. It becomes our natural key. The same with zip codes and everything else. Somebody at one time arbitrarily assigned an integer, but that integer sticks, and now that becomes a natural key. Purchase order numbers would be another one. Right. The second thing I would highlight to you is never create keys with metadata. This is such a temptation where we take a product and or something that we're dealing with, we take the metadata of that thing and we add it together into a composite key and we say, okay, this becomes the key. And look, it's handy because instead of going to the object itself or the message itself or the event itself, I can just look at its key and extract data. How clever am I? Well, you've just painted yourself into a corner big time. That's going to cause you pain and suffering, or more likely the people that take over your system, because the metadata will change over time. And then what are you going to do, right? So for instance, if I had if I created a composite key of my users and part of the key was the country of the user, right? And then the username or something like that. Well, what happens when my user moves countries? What if the person decides to move from the Ukraine to Poland, right? Now what have I done? Now the metadata, do I change the metadata? Now I've changed the key? It's maddening. Just little pet peeve of mine, don't do it. All right, enough on keys. But here's not enough on keys. I got one more thing to talk about. UUIDs. universal unique identifiers. You're going to see these in stream processing. You have to have them in stream processing. And the reason is that sequential identifiers will not work in a distributed environment. If I have 3 processors running in parallel, what integer do they assign? Right? If I say, okay, this processor is going to only generate numbers that start with 3 million, and this one's going to do with 4 million, and this one's going to do with 5 million. Well, first off, I'm going to have a whole lot of numbers that aren't assigned. I'm going to run out of numbers. What happens if system 3 goes down, the one that was assigning 3 millions goes down, and I bring it up? Where do I start numbering again? You're just going to have to deal with the fact that sequentially identifying things is not going to work in a distributed environment. But we have UUIDs, right? It's a 128-bit number, and you have frameworks in all your languages. Linux comes with, out of the box, with a UUID generator. And you don't have to worry about collisions, right? The math is you could create 1 billion UUIDs per second, and you would maybe in 85 years have a collision. So for the foreseeable future, I know when you're older, they're going to have a UUID collision crisis that you're all going to have to rewrite all your systems for. All right, just like we had the 2000 bug back in 1999. But for the foreseeable future, UUIDs are the way to identify everything with a generated key. And so when we talk about partitioning on a key, how do we do that? I talked about, the range of keys and round robining and sourcing and partitioning by key. The most common way, almost all the time you're going to deal with partitioning, you're going to deal with a partition by hash mod. And what you really want to do is make sure that the objective is that every event with the same key is on the same partition. That's your objective. Because remember that the number one objective of parallel processing is to make sure that 2 different processors are not modifying the same state. Right? So if a key is associated with the state and the processor is reading things from the stream, then the objective is that the same key must always go to the same partition. And how do you achieve that? It's this simple. You take a hash of whatever your key is, and then you take a modulus of that hash based on the number of partitions you have. So for instance, let's say I have a natural key and the key comes up Amsterdam. And then I run a hash method on this. And a hash method just simply takes any object and returns an integer, right? And it will always return the same integer. So if I give this hash function Amsterdam, it'll always return the same integer. But if I gave it Amsterdams, or Amsterdam with a U, it will create a different hash integer, right? So then if there's 10 partitions, then all I do is I divide by 10 and take the remainder. That's what modulus means. And that tells me what partition that this particular record should go on. It's that simple. Hash mod. That's how you partition your data and make sure that the records of the same key are always on the same partition. Another advantage of this is balancing, right? you don't want, let me just jump back. You don't want these partitions you want these partitions to be as balanced as possible. So you don't want 80% of the messages going on partition 1 and then 10% going on partitions 2 and 3. You want as close to 33% on each of the partitions to balance your process flow, right? So the hash mod method of partitioning achieves that for you. All right. So when joining partitions, it can be tricky, right? So here we have two different streams, and the streams have, the first stream has 2 partitions and the second stream has 3 partitions. And I want to join based on color, right? So the color indicates a key match. So the first thing to do is to do you take the minor stream, the stream that has less data, and you duplicate it on every processor, right? So each processor takes each partition of the upper stream. Does that make sense? So in essence, P1 is consuming all the partitions of the square stream, and P2 is consuming all the partitions of the square stream, and same with P3. And then P1 only consumes 1 partition of the triangle stream, same with P2 and P3. And as a result, we're able to join. Does that make sense? All right. Now, note that the problem would be exactly the same even if the partitions were sorted on the square stream. We would still have to replicate all of the square stream in each processor because they're not sorted in the other stream. And one option then would be to repartition the triangle stream. And if you do this, right, if you take a processor and I take the 3 streams, the 3 partitions of the triangle stream, and I repartition them so that they're sorted, then I can make sure of a join by just reading all the blues in P2 and all the reds in P3. So think about it as in this blue color and this red color, you can think of it as that hash mod, right? If it doesn't matter where the key is so long as it's consistently there. So if I use the same hash mod on the square stream for partitioning and the triangle stream for partitioning, then I will know that the blue will actually be blue, that a given Amsterdam key will be in the blue stream on the square and the blue partition on the squares and the blue partition in the triangles, because we use the exact same hash mod for partitioning. So I'm assured that P2 will be processing Amsterdam. This may not be the best way of explaining this, but I've tried. So, the last thing about partitions that I'll point out is that you really want to do a partition of partitions when dealing with your data. at any significance. And the reason is that scaling should be elastic. That you can never, that you want to be able at some point in the future add nodes or reduce nodes of your processor. If you have 4 processors and you created 4 partitions, and then you want to add 2 more processors, you have to go back and repartition all that stream, which can be exceedingly expensive, especially if you have to do it with historical data. If, however, you have 4 processors but 40 partitions, and each one of the processors is consuming 10 partitions, right? Then expanding becomes much less expensive. Then when I add 2 more processors, then I can just rebalance very simply, right? I can take 2 from each of the existing processors and have the processors stop processing 2 of those or 3 of those, 3 of them, and then have one of the new processors pick up those partitions. This is called repartitioning. And this is how you scale up and scale down, is repartitioning. But if your number of partitions is not a multiple of your processors, repartitioning becomes very painful. Does that make sense? Any questions on partitioning and joining on partition? All right, well, we got a few minutes left, and I wanted to go through a quick real-world example that is very near and dear to my heart. So you can start thinking about, we've talked about very classic stuff of processing stocks and trades. And let's face it, banks spend a lot of money on IT, so I'm betting at least somebody in this classroom is going to be working for a bank doing processing of trades. It's just inevitable. But let's talk about something a little sexier, which is sensor data fusion, which is inherently a streaming processing, which in the past has been done as batch processing. And I'm going to give you a very real world example. This is the system representation of a spy camera on a drone, right? Or a camera on a drone. We don't necessarily need to be spying with drones. We could be looking at agriculture or rooftops. It doesn't have to be naughty. So you have an inertial measurement unit, a GPS, a global positioning system, a gimbal, which represents the turning of this camera. And then this camera has an XYZ, it has a frame of reference, right? A coordinate frame of reference. And each one of these sensors is sampling at a different time, right? So your gimbal may be coming out very, very quick. Your GPS may be coming out a little bit slower. Your IMU may be a little bit slower still. And then your camera is a scanning camera, right? So we're normally used to dealing with an instantaneous camera, but those have low fidelity. So a higher fidelity camera will scan, which means that the sensor time is spread over time. So in the legacy world, what we would do is we would take a picture and then we would just pick one of the values almost arbitrarily for the lat long, altitude, pitch, roll, and heading, right? So that we could figure out where this picture, what this picture is looking at, to resolve it. Well, the problem there is that we've just arbitrarily picked sensor data. And so we've lost all the fidelity of the sensor data because we're batching it instead of streaming it. So we've taken what is naturally a streaming process, forced it into a batch process because of legacy constraints. And those legacy constraints, those actually existed in Vietnam, I mean, in the 70s, but today we don't need to do things that way. We need to process the data differently. So here what you would do is treat it as a stream. So you take that data and you interweave it, right? So here we're kind of said, you know, at timestamp 2456, we get a lat long reading from the GPS. And the image is continually scanning. And then at 2762, we get a pitch roll and heading from, and then, which is a different sensor reading. But the image continues to scan. And you can see how the data is, interleafed in reality. So what we can do is for each point of that, each line of that camera scan, we can get a very clear interpolation, a very accurate interpolation of this other sensors as they apply to that, that point in time. So, for instance, for this, for the images time at 2789, we can interpolate between the pitch, roll, and heading readings at 2762 and 2910. All right, but think about how that concept of how you would process this data takes into account all the things that you were just talking about. How the windowing, right? Where do we emit that calculation from one pitch roll heading event to another pitch rolling heading event, and join that with the stream of the pitch roll heading stream of events with the image stream of events? Because there's got to be that windowing of calculation that makes that happen. All right, so this would be a good place to have a review slide, but I don't have one, unfortunately. What I'll say is just real quick, go over the things that we talked about, right? We talked about how streaming more accurately mimics the real world. How we process using sources, sinks, and operators, and we form them into directed acyclical graphs. That streams are different because they are infinite, continuous processing. There is no now, and you're dealing with eventual consistency. We talked about time skew. We talked about message delivery being in 3 types, right? There's at most once delivery, at least once delivery, and exactly once delivery. We talked about windowing, how there's fixed windowing, session windowing, and sliding windowing. And we talked about joins and how there are inner joins, left joins, and outer joins, and that the results of those are very different. We talked about how you scale streaming processing by running in parallel. You run in parallel by partitioning the streams, and that you partition in 3 ways, either by source, round robin, or key. And that the most common way of partitioning is by key, and the easiest way to do that is to partition by hash mod, right? So that is the concepts, the base concepts that I wanted to review of stream programming. And then it's a lot of hand waving now, but it becomes very practical when you actually start implementing this code. So we've got 5 minutes left on the clock. I'll open it up for any questions that you may have.
Can you hear me?
Yes.
I have a question about choosing a number of partitions. So as changing this number is costly when you have a lot of data, you should choose number at start and then continues to rebase. I mean, this example with 4 and 6 partitions in your slides. So we can choose easily a big amount of chunks, partitions at start, but it will be costly to manage. And question is how to find balance, not low amount of partitions and not so big to manage, as you have said.
Yes, so I'm trying to share my screen again. All right, you guys can see that slide again?
Yeah, the slide. So here we have 40 chunks.
40 partitions, yep, on the stream.
40 partitions, yes, and 4 processes. Then we can expand it to 6.
Correct.
Yes, but if we choose at start a big amount of partitions, million, for example, it will be hard to manage.
Right. You don't want a million. Okay, so yeah, it depends. What I would say is create a number of partitions that is a multiple of your expected processors, and your number of expected processors is going to depend on how much compute power you have, how large the volume is, how long it takes, what your SLA is for delivery. You know, I want to be able to process this data in less than, 100 milliseconds. So there's a lot of design parameters that go into scaling that say how many processes am I going to have. But in reality, you're not going to have 1 million processors. You're probably not even going to have 1,000 processors. You're probably going to have the order of 5 to 100, right? So just have the number of partitions be a realistic multiple of your processors. And I think a realistic multiple is 10. So if beginning the system, if you say, okay, when we go into production of this thing, I think we're going to need about 20 processors to meet requirements. And I've done this based on by testing how long the calculation is, and I know how big this data is and how I know how fast the data arrives. Then if you're going to be doing 20 processors, then do 200 partitions.
But
you don't want 1 million partitions.
Yes, okay, but for example, I store data from Snapshot at the beginning when Snapshot wasn't so popular, and I decided to have a small amount of partitions, for example, 100. But then, boom, and Snapshot are so popular, and the amount of stream data are amazing. And I need to count thousands of partitions. So the only case is to re-index, create new partitions. Yeah.
Right, and one solution there is, yeah, you would have to repartition. There are going to be cases where, everything is a trade-off, right? That's what engineering is. Engineering is not optimizing. Engineering is compromising. Engineering is making the best possible trade-off. And so you're going to have to make a decision that kind of handles your growth, but meets your needs right now, right? And so, yes, you will be faced with, if you have a successful system, you're going to be faced with repartitioning. There are several ways to do that. The easiest way is to create a new stream that has the larger partitioning, right? And point your systems to the new stream, and then repartition the old stream onto the new stream. Does that make sense?
Yeah, thanks.
So you would get your historical data on there by repartitioning, but you don't, because we know that things occur out of time, you could do that in real time. You could just start running the new system to the new partition and then play the history back into the, from the old partition into the new partition and have that there. So, good question.
Thanks.
Any other questions? All right, well, we're at the hour. We hit our time mark perfectly. I appreciate your attention, and I look forward to seeing you in the final lecture, which will be about Kappa architecture, where we take this one step further to the state of the art. All right, thank you again for being here.